Alright, in this section we're going to finish up Chapter 2 by going over infinite limits. And we're going to determine infinite limits from the left and the right and find and sketch vertical asymptotes of the graph of a function. Now remember, a limit is, infinity is not a limit. That would be unbounded behavior. So what we're talking about here is the behavior of functions. Does our function head to positive infinity or to negative infinity as we approach some x value? So infinite limits. Let f be the function given by. Here we have our numerator is a constant, just a 3, and our denominator is x minus 2. So we're going to be suspicious about, of course, the number 2. What happens as we get closer and closer to that number? So if we do this by the table method, like we did limits way back in section 2.2, if we plug in the function into the y-editor and we plug in 1.5, our calculator spits out a negative 6. If we plug in 1.9, we get closer to 2, our calculator will spit out a negative 30. 1.99, now we get a negative 300. Ooh, we're getting big. 1.999 is negative 3,000. Let's see what happens as we approach from the other side. Here's our 2. We're going to approach from numbers greater than 2, or our right-handed limit. Plug in the 2.5, you get positive 6. Plug in 2.1, you get 30. 2.01, 300. 2.001, 3,000. So look at that, we're approaching two different numbers from the left and the right, so we know this limit doesn't exist, and we have unbounded behavior from the left, and we have unbounded behavior from the right. And since we're approaching a negative number, negative 6, 30, 300, 3,000, we're getting bigger and bigger negative numbers, we're going to say f of x decreases without bound. Decreases without bound. We're heading toward negative infinity. But as we approach from the other side, 6, 30, 300, 3,000, we're going to say f of x increases without bound. Increase without bound. So the limit doesn't exist, it's unbounded behavior, but we're interested, is it positive infinity or is it negative infinity? So as we approach from the right, positive infinity. Just if I wanted to do a quick sketch of the graph, I know here at an x value of 2, I'm going to have an asymptote. Oop, that was pretty terrible. So at 2, we have an asymptote. As we approach from the left-hand side, we're heading down toward negative infinity. As we approach from the right-hand side, we're headed up to positive infinity. And is this ever going to touch the x-axis? It's just going to become smaller and smaller fractions, so the farther out we go, we're probably not going to cross the x-axis at all. And I think I got a better picture that came. Yeah, there we go. Oops. And there it is. As we're coming in from the left-hand side, we're approaching that asymptote. The closer we get, the quicker we drop off. As we approach 2 from the numbers above, from the right-hand side, we're heading up higher and higher up toward positive infinity. Going to get close to that asymptote, but never touch it. So here in example 1, we're just going to determine infinite limits just by looking at the graphs. So determine the limit of each function as shown in the figure as x approaches 1 from the left and the right. Okay, for the first one here, letter A, let's look at the limit from the left. The limit as x approaches 1 from the left-hand side of f of x. So here's our 1. We're approaching from the left-hand side. We can see that the graph is headed up toward positive infinity. And the other one, the limit as x approaches 1 from the right, from the plus side. So now here's again is 1. We're on the plus side. We're heading up again. As we get closer and closer, we can see graphically that we're also headed off to positive infinity. And the reason that happens is, here's our function. Our denominator is squared. X minus 1, no matter what happens in the parentheses, whether it's positive or negative, we're going to square it. And we're dividing that into a finite numerator that's just 1 divided by something that's always positive, and as it gets infinitely small and we divide that into 1, that's going to give us an answer infinitely big. So we're heading up to positive infinity for both of those. If we would maybe put a negative in the numerator, that would give us always a negative answer, and our graph would look just like it was flipped around the x-axis. We would, this looks like a volcano that's opening up. We would have the same thing flipped around. It would look like a volcano opening down if there was a negative in that numerator or 1 in that denominator. So sometimes, as you approach an asymptote, you're headed in the same direction, both to positive infinity or both to negative infinity. Here in part B, we're going to get one of each. So the limit as x approaches 1 from the left of this function, and now it's negative 1 over x minus 1. So as we approach here from the left-hand side, our denominator is going to get, very, very small as we approach 1 from the left-hand side, and it's going to be negative, and we're going to divide that into the negative 1 numerator, so that is going to take off toward positive infinity. And as we look at the right-hand limit, the limit as x approaches 1 from the plus side. So we're approaching, our number, I like to think maybe, something close, 1.1. 1.1 minus 1 in our denominator is positive, and we're dividing that into a numerator that's always negative. Positive divided by, or negative divided by positive is negative. So as we get closer to the asymptote, we're headed off toward negative infinity. So really a lot to figure out this infinite behavior, or unbounded behavior, is you're going to break down your quotient into either a positive divided by positive, you'd head toward positive infinity. Positive divided by negative, you're headed toward negative infinity, and so on and so forth. So vertical asymptotes. If it were possible to extend the graphs from the previous figures toward positive and negative infinity, you'd see that each graph becomes arbitrarily close to the vertical line x is 1. This line is a vertical asymptote of the graph of f. You'll study other types of asymptotes in later sections. So here's our definition. If f of x, our function, approaches infinity or to negative infinity, as x approaches c from the right or the left, the line at x equals c is a vertical asymptote of our graph of the function f. And theorem 114 says let f and g be continuous on an open interval containing point c, as long as f of c does not equal 0, and g of c equals 0, then there exists an open interval containing c such that g of x does not equal 0 for x not equal to c in that interval. And the graph of the function given by h of x is our f of x function divided by g of x. It has a vertical asymptote at that point x equals c. Let's talk about that. That it can be a little confusing here. Let's break it down. F and g are continuous functions if f of c does not equal 0. So when we plug c in, our numerator does not equal 0. The numerator is non-zero. And g of c is equal to 0. So if we plug that same point c into the denominator function, we do get equal to 0. So our numerator is not 0, but our denominator is 0. Then the graph given by that quotient, that division of function, is going to have a vertical asymptote at that point. Non-zero denominator, 0 denominator means vertical asymptote. So here in example 2, they're asking us to determine all vertical asymptotes of the graph of each function. So let's see what's going on here. Our numerator is never equal to 0. So what we want to find out is what value of x is going to give us a value of 0 down here. Well, if you want, you could set, that equal to 0, divide both sides by 2, and then you get x plus 1 is 0, minus 1 from both sides. We're going to have an asymptote at negative 1. So there's our asymptote, and actually, they didn't ask us to do it, but let's figure out the behavior on each side of that asymptote. So this is happening at negative 1. Let's pick in a number, close to negative 1, a little bit on the left-hand side here, like negative 1.1. If I plug in for this x negative 1.1 and add 1 to it, that's going to be a small negative number. Times 2 makes the whole denominator negative, so we have positive divided by negative, which means we're going to head for negative infinity. If we hop on to the other side, a number a little bit closer to 0 than negative 1 would be negative 0.9. If I put negative 0.9 there and add it to 1, that makes what's in the parentheses positive, times 2 is positive, divided into a positive 1 is positive divided by positive. So as I approach from the other side, from the right-hand side, I'm heading toward positive infinity. And that's what our asymptote and graphs will roughly look like. And let's make sure I didn't mess anything up. Yeah, there it is. As we approach from the left, negative infinity. Approach that asymptote from the right, positive infinity. It all comes down to signs. Now let's see what's going on here in letter B. Let's look at our numerator, x squared plus 1. X squared plus 1, no matter what we plug in for x, even a negative, we square it, that turns it positive. We add another 1. Our numerator is always positive. So now we got to think, okay, when does that denominator equal 0? X squared minus 1. Well, x squared minus 1 factors into x plus 1, x minus 1. And we set that equal to 0, and we get two x values, plus and minus 1. So here it looks like we're going to have two asymptotes at plus 1 and another one at minus 1. And let's plug in, draw some dots here for our asymptotes. So we're going to check the behavior on each side of those asymptotes. So let's approach here from a little bit under 1, or this negative 1. So maybe, I'm thinking in my head at negative 1.1. If I plug negative 1.1 in here, remember that now the numerator is always positive, so we don't have to check that anymore. If I plug in here for this x squared, negative 1.1, and square it, I'm going to get a number a little bit bigger than 1, and a number bigger than 1 minus 1 is still positive. So we get positive divided by positive. As we approach from this side, we're headed to positive infinity. Now let's see as we approach from over here. This would be negative 0.9. Numerator again, always positive. Here would be negative 0.9 squared. That would be positive 0.81. Minus 1 would give us a negative output. Positive divided by negative is negative. And we're going to be heading down this way. So now we're over here at positive 1. Let's check our behavior on each side of that. Here it would just do a positive 0.9. Positive 0.9 squared give us the same value as here. A number a little bit smaller than 1 minus 1 is negative. Positive divided by negative is negative. So we're going, I don't like that very much there. We're going down and approaching that asymptote. Last one to check, a number a little bit bigger than 1, 1.1. 1.1 squared is bigger than 1, minus 1 is positive. So as we approach from the right, we're heading up toward positive infinity. So there we are with two asymptotes. We got something happening to the left, we got something going on between the asymptotes, and we got something happening to the right. And let's see if I messed any of that graph up. No, looks pretty good. Just the rough sketch of it. As we approach the first asymptote from the left, positive infinity. In between the asymptotes, we're headed toward negative infinity. And from the right, coming toward 1, we're heading up to positive infinity. All right, last one. Part C. Now it's asking us to find the asymptotes. Is this really even a calc? Well, yeah, we're just talking about asymptotes. Cotan function. So we just got to think back to pre-calc. I'll chop this up here into a pi and a 2 pi, negative pi, negative 2 pi. I always remember the tan function goes through the origin up to the right, down to the left, with asymptotes at plus and minus half pi. And cotan, we reverse the graph. So instead of going up to the right, down to the left, it's up to the left, down to the right, and we no longer go through the origin. We're going to shift that all over 1/2 pi. So actually our x-intercept is going to be half pi, and we go up to the left for a half pi until we hit our asymptote, down to the right, half pi till we hit our asymptote. So here, remember for cotan, our asymptotes occur at the y-axis, and every pi on either side. Positive and negative, positive and negative. And then in the middle of each of those, here at 3/2 pi, we have an x-intercept, up to the left, down to the right. Negative half pi, x-intercept, up to the left, down to the right. Negative 3/2 pi, up to the left, down to the right. So there's all our vertical asymptotes, and that would be, we could even write that as, so determine all vertical asymptotes. We would start at 0 plus and minus some integer n times pi. That would give us all the asymptotes to the left or to the right. And now that I think about it, I guess another way, I'm very graphical in my thinking, another non-graphical way to figure out that, where do the asymptotes of cotan lie? Well, remember, cotan of x is equal to cos of x over the sine of x. And the asymptotes are going to occur when the numerator is a non-zero number and the denominator is equal to 0. So we got to think, where does sine equal 0? If we think about the sine wave, we start at 0, we go up and down and we cross at pi. And then we go under and back up and we cross at 2 pi. And then that just repeats, and it is reflected onto the left side of the x-axis, or to the left side of the y-axis. So those would be the points where the asymptotes exist. If you want to think about that as cos over sine, I guess would be an alternate method. And on to example 3. It says here, determine all the vertical asymptotes of the graph of this function. So probably a common misconception here would be to say, okay, I'm going to take that denominator and I'm going to set it equal to 0. Or I can factor it into x plus 2 and x minus 2, and I'm going to set each of those to 0, and I'm going to have asymptotes at plus or minus 2. That'd be a real common wrong turn to take on this problem. Remember, we can have asymptotes or discontinuities, and some of those discontinuities are removable. So if I look at that denominator and I think, okay, I can factor that, that's a sum and a difference, x plus 2, x minus 2. I don't want to just jump to setting those equal to 0. I want to factor that numerator also. So let's see, can we factor that numerator down? Yes, we can, into an x plus 4 and an x minus 2. So now that we've factored the numerator, we can see a common term. So we can cancel that out. And remember, when we factor and cancel out, that's like sort of paving over a pothole or removing a discontinuity. So right now we've found a removable discontinuity at x equals 2. So that takes care of that part. Now we've taken our original function f of x and we've broken it down into just this simpler function. Okay, now where are we going to have a problem dividing by 0 here? Well, if I plug in a negative 2, I get a 0 denominator and a non-zero numerator. So we're going to have a vertical asymptote, and I'm just going to abbreviate VA, a vertical asymptote at negative 2. So let's see if we can come up with a graph. I guess the directions say determine all vertical asymptotes, and I guess we found the vertical asymptote, and we could stop right there, but I'm having too much fun. So we know there's a vertical asymptote here at negative 2, and it's going to be dot, 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 dot. There's our asymptote. Let's figure out as we approach from numbers a little bit less than that. We're going to have, if I plug in negative 2.1. into this function here, if I have negative 2.1 plus 2, that means my denominator is negative. And if I put the same negative 2.1 in here plus 4, that's positive. So for that, it means we're going to be heading off toward negative infinity. Our numerator is positive, our denominator is negative, so we are going to be heading for negative infinity down this way. And then from the other side, if I approached here from negative 1.9, negative 1.9, and for that x, negative 1.9 plus 2 would be positive, and negative 1.9 plus 4 would also be positive. So over here we're going to be heading for positive infinity. And remember, we have a removable discontinuity at x is 2. So somewhere over here on this side at 2, we would have a hole in the graph. When we factored and canceled that common factor out, that's where we sort of paved over that hole. So that's roughly what our graph should look like. Let's see here. Yeah, there we go. As we approach our asymptote from the left, we're headed to negative infinity. From the right, we're headed to positive infinity, increasing without bound. At that x value of positive 2, we have an undefined point. We have a discontinuity. All right, and here in example 4. Here in example 4, it says, find each limit. We're determining infinite limits. We have the same function, x squared minus 3x over x minus 1, and we're approaching 1 from the left, and we're approaching 1 from the right. So let's see here, as we approach 1 from the left-hand side, or numbers a little bit farther away from 0 than 1, I'm thinking 1 from the left, 0.9. So if I plug in 0.9, I'm going to get 0.81 when I square it. Minus 3 times 0.9 would be 2.7. Divided by 0.9 minus 1, 0.9 minus 1. And here, remember, we're mostly worried about sign. 0.81 minus 2 is definitely going to give us a negative. 0.9 minus 1 is also a negative. And a negative divided by negative is a positive. So we're going to be heading for positive infinity. The limit of this function as x approaches 1 from the left side, and I'm not going to rewrite the whole function, I'll just write f of x. The limit as we approach 1 from the left of f of x is negative divided by negative, which tells us we're heading off to positive infinity. Let's check out the other side and see what's going on. We're approaching 1 from numbers a little bit bigger than 1. So I'm thinking here in my head 1.1. Well, 1.1 squared would be 1.21, I believe, minus 3 times 1.1 would be 3.3, divided by 1.1 minus 1. So 1.1 or 1 point anything minus 3.3 is definitely going to be negative. 1.1 minus 1 is positive. Negative divided by positive is negative. So our limit as we approach 1 from the right-hand side of our function is equal to negative infinity. And let's see here graphically what would that look like. So here is negative 1. That is our asymptote, where we would be dividing by 0. Non-zero numerator, 0 denominator means we're going to have a vertical asymptote. As we approached from the left side, we went up to positive infinity. As we approached from the right side, we're heading down to negative infinity. And I see over here I do have a technology pitfall box. Those are real important, especially when you're taking the AP test. You want to make sure the calculator doesn't lead you down the wrong path. There we go. When using a graphing calculator or graphing software, be careful to interpret correctly the graph of a function with a vertical asymptote. Graphing utilities often have difficulty drawing these types of graphs. And here we got some properties of infinite limits, and these might be very similar to our properties of limits and other stuff with properties of continuity. Point C, let C and L be real numbers, and let functions f and g be functions such that the limit of the f function is infinity, and the limit of the g function is L. So here we have a limit, it's just a number. Here we have an infinite limit. So if we add them together, think about it like this. F of x is infinity. If we have infinity plus or minus some finite number L, well, infinity plus a number is still infinity, or infinity minus some little number is still infinity. What about the product of them? If we have f of x times g of x, that's sort of like saying infinity times some number L. Or maybe let's just plug in a number for L. If it's positive, infinity times 3 is still infinity. If our finite number, if our limit is a negative number, f of x times g of x would be infinity times negative 4. That would make it negative infinity. And for the quotients, if we are dividing, this is an important one. G of x is finite. So g of x is just some number like 3 or 10 or even 1,000,000. And we are dividing that by f of x, which is infinity. 3 divided by infinity, what number is that going to approach? It's going to approach 0. Think about it like this. 3 divided by 1,000,000 is a small fraction, and we're going to make our denominator get bigger and bigger. 3 divided by 100 billion, or 100 trillion, something huge. As that denominator gets bigger and bigger and bigger, we're dividing it into a finite numerator. That's going to be a fraction that gets smaller and smaller and smaller, and it's going to approach 0. So a finite numerator divided by an infinitely large denominator is going to approach 0. Similar properties hold for one-sided limits and for functions which the limit of f of x approaches c is negative infinity. Okay, here in example 5, they're asking us to determine some limits. The limit as x approaches 0 of 1 plus 1 divided by x squared. So we know the limit as x approaches 0 of 1 is going to be 1 plus what happens when we get this denominator very, very close to 0. If it's 1 divided by 1, we're going to get 1, but as we get closer and closer to 0, think about 0.1. 1 divided by 0.1 would be 10. 1 divided by 0.01 would be 100. 1 divided by 0.001 would be 1,000. 0.0001 would be 10,000. The closer we get that denominator equal to 0, and of course we're squaring it, it'll get even smaller. 1 divided by an infinitely small number is going to equal infinity. And 1 plus infinity is equal to infinity. And if we were making that infinitely large, 1 divided by an infinitely large denominator would approach 0. 1 divided by an infinitely small denominator is going to equal infinity. Let's see what's happening here in number 2. Or letter B, I mean. Let's look at the numerator by itself. As x approaches 1 from the left-hand side, from numbers a little bit less than 1. So we're going to square that and add 1 to it. That's always going to be positive. And we could do the direct substitution. 1 squared plus 1 is 2. So it's going to be a positive 2. And as we approach 1 from the left-hand side down here in the denominator, if I plug that 1 in, it's going to be the cotan of pi. And we got to think about our cotan graph. Here is pi. We're approaching 1 from the left. Let's see, our cotan graph is going to go up to the right, down to the left. So that is going to be negative infinity. We're heading off toward negative infinity. And here it doesn't matter if our infinity is positive or negative. We have a finite numerator divided by an infinitely large denominator. That is going to head us toward 0. And in the last one here, we just have 3 times the cotan of x, and we're approaching 0 from the plus side. So let's see here again our basic cotan graph. As we approach 0, that is the y-axis, and the cotan graph is going to go up to the right and down to the left. So, the 3 we're just sort of multiplying. It's going to be 3 times. As we approach 0 from the plus side, we're approaching 0 from the plus side, we're heading toward positive infinity, and 3 times infinity is infinity. And from our previous page, 3 times infinity is infinity. We were just applying this property here. Our L, our limit, was positive, or for the one function, it was 3 times infinity, which gives us an output of infinity, or a limit of infinity. And that's it. That is the end of section 2.5. That's all we're doing in chapter 2. So the test is coming up.